For centuries, the deep ocean was the final blank space on our map, a realm of pure conjecture, where cartographers sketched sea monsters and wrote just 3 words: "Here be dragons." It was a liquid abyss, believed to be a frozen, lifeless desert, a silent, eternal midnight. Then, in 1872, a ship named HMS Challenger set sail to erase that blank space. Its mission: to plumb the depths of the impossible. They found the dragons. But they were not the monsters we imagined. The Challenger's voyage began a story we are only now finishing, because we have just learned a terrifying and magnificent truth. The ocean floor is not the bottom. It is a ceiling. And below it, in a labyrinth of secret, sunless caves, thrives a breathing, pulsating, hidden ocean, a world beneath the world. This is the story of the ocean that shouldn't exist on any map, a discovery that redefines life itself. To follow this journey into the heart of the unknown, make sure you're subscribed. They set sail from Portsmouth, England, on a cold December morning in 1872, with a mission that bordered on madness: to map the unmappable, to measure the immeasurable. The HMS Challenger was a British naval vessel stripped of its guns, its hull converted into a floating laboratory. Its arsenal? 12 miles of Italian hemp rope, lead weights, and a bottomless curiosity. For 3.5 years, this ship of wood and canvas would wage war against the greatest unknown on the planet, the deep sea itself. The prevailing theory of the day was the azoic hypothesis, a simple, sterile belief that life could not exist below 300 fathoms. The abyss was a frozen, lightless, and lifeless desert. The Challenger was sent to prove it. Their method was one of brutal, simple force. They would lower their dredges and sounding lines for hours, sometimes days, into the black. The rope would strain, the ship would list, and men would wait. What emerged from those depths defied all expectation. Not a barren wasteland, but a menagerie of the bizarre. They hauled up creatures that seemed ripped from a fever dream: blind fish with needle-sharp teeth, ghostly white octopuses, and organisms that bled green. Each haul was a revolution pulled from the deep. The azoic hypothesis was shattered. The deep sea was not dead. It was teeming. But in solving one mystery, the scientists of the Challenger created a deeper, more profound one. They had mapped the surface of the abyss, but they could only guess at what lay beneath its floor. The core samples they pulled from the seabed were not just mud and ooze. They were hints of a world below, a world of heat and rock, utterly inaccessible to their miles of rope. The legacy of the Challenger expedition is not found in a single discovery, but in a paradigm shift. It was the moment we stopped imagining the ocean as a mere surface for ships and began to understand it as a 3-dimensional world, with its own mountains, valleys, and alien inhabitants. They gave us the first true map of the ocean floor, revealing the mid-Atlantic ridge, a submerged mountain range that hinted at the planet's volatile geology. But for all they revealed, the greatest secret remained locked away, just beyond their reach. They had proven life in the deep. They could never have conceived of life under it. Their voyage asked a question they couldn't possibly answer. If the cold, dark water is this full of life, what wonders are hiding in the warm, dark rock below? The men of the Challenger had opened a door, but they could not step through it. They left behind a world of questions, written in the language of dredged mud and preserved specimens. For nearly a century, their findings gathered dust in museum cabinets, their deepest implications waiting for technology to catch up to their ambition. The ocean floor remained what it had always been, a vast, blank canvas for our imagination. We filled it with myths of lost cities and leviathans, but the truth, it would turn out, was stranger than any myth. The central question that emerged from the Challenger's wake was one of energy. The sun's light penetrates only the topmost layer of the ocean. Below that, there is only cold and dark. How could complex ecosystems survive down here, cut off from the fundamental engine of all life on Earth? The simple answer was that they couldn't. They had to be fragile, starving communities, clinging to existence on the faint drizzle of dead plankton and organic debris that settled from the world above. This marine snow was thought to be the only possible food source. The deep sea was a biological desert, with a few scavengers waiting for scraps to fall from the table. It was a logical, elegant, and completely wrong conclusion. Then, in the 1970s, a new generation of explorers took up the Challenger's mantle. They were not in wooden ships, but in titanium-hulled submersibles like Alvin, capable of descending directly into the abyss. They went to places the Challenger could only dream of, to the great rift valleys that tear through the ocean floor. And there, in the crushing silence, they found the dragons. They were not monsters of flesh and blood, but monuments of stone and heat. They discovered towering chimneys, 20 feet high, belching black, superheated water rich with chemicals. They called them smokers, and around them, in the water that should have been lethal, thrived a riot of life. Vast gardens of ghostly white tube worms, fields of giant clams, and swarms of blind shrimp. This was the moment the old world ended. The life here did not run on sunlight. It ran on poison. The process is called chemosynthesis, life from chemicals. Where photosynthesis uses light energy, chemosynthesis uses the chemical energy of hydrogen sulfide, a toxic gas that spews from the Earth's interior. The tube worms, the clams, the bacteria, they all thrive on this toxic brew. It was a second genesis, a parallel tree of life flourishing in total isolation. The Challenger had found life in the deep. Alvin found an entire new way to be alive. But even this stunning discovery was only the beginning. Because these vent ecosystems were isolated, like islands, and a question haunted the scientists who studied them. How do life forms from one vent colony reach another, across miles of barren seafloor? The larvae of these creatures are fragile. The open ocean is a death sentence. So how do they travel? The answer was not in the water. It was underneath it. The pioneers of the Challenger mapped the contours of the deep. The pioneers of Alvin discovered its oases. But they were all looking in the wrong place. The final frontier was not on the seafloor. It was beneath it. The true secret was hidden in the rock itself, in a labyrinth of caves so vast it constitutes a second ocean. A world beneath the world, whose discovery would change everything we thought we knew about our planet. The discovery of the hydrothermal vents in 1977 was more than a discovery. It was an upheaval. It tore up the textbook and forced us to write a new one. Here was an ecosystem that fundamentally rejected everything we thought we knew. It thrived in total darkness, under pressures that would crush a nuclear submarine, fueled not by the sun, but by the toxic, volcanic breath of the planet itself. The scientists who first saw it through the portholes of Alvin were not just looking at new life. They were looking at a new logic for life. The foundation of this world is chemosynthesis, a process where bacteria use chemicals, not sunlight, for energy. These bacteria form the base of a food web that supports towering worms, armored clams, and blind shrimp. It is a world built on a foundation of poison, but for all its wonder, this discovery created a new, equally profound mystery. Vent fields are not continuous. They are isolated oases, separated by miles of barren, abyssal plain. They are born when volcanic activity cracks open the seafloor, and they die when that activity ceases, their lifeblood of hot water shutting off. This presented scientists with a seemingly impossible puzzle. How do these communities colonize new vents? The larvae of these creatures are microscopic and delicate. The open ocean between vents is a cold, foodless expanse, a certain death sentence for them. Yet, new vents, erupting in isolation, are quickly populated. The larvae are arriving from somewhere. But how? The most radical hypothesis was as simple as it was unbelievable. Perhaps the larvae weren't traveling through the deadly open water at all. Perhaps they were traveling under it. The theory proposed a subseafloor ecosystem, a labyrinth of cracks and cavities in the upper volcanic crust, flooded with warm, chemical-rich water. A subterranean highway, running for hundreds of miles beneath the ocean floor. To the mainstream scientific community, this was borderline fantasy. The evidence was circumstantial. The ocean crust was considered a solid, impermeable layer, not a Swiss cheese of hidden passages. The skeptics held firm. Where was the proof? Where was the data? Show us this hidden world. For decades, they couldn't. The pursuit of this ghost ecosystem became a grand scientific obsession. It was a theory that could explain everything, yet could not be seen. Drilling programs would bring up cores of rock from the seafloor, and occasionally, deep within the basalt, scientists would find strange fossilized tunnels, biotextures that looked like they had been etched by microbes. But these were fossils, ghosts of a past world. The question remained, was it alive today? Was there a living, breathing, connected world right under our submersibles, a world we were blindly passing over? Could an entire ecosystem be hiding in the basement of the ocean, and we never knew? The proof would not come from a single dramatic dive. It would come from a clever, patient experiment designed to listen for the whispers of a hidden world. The central figure in this next act of the story is Dr. Monica Bright, a biologist whose work would bridge the gap between radical theory and tangible proof. Her team traveled to a known vent field in the Pacific, to a specific area known as the Fava Flow. Here, the volcanic crust was young and porous, the perfect place to lay a trap. Their experiment was elegant in its simplicity. They would place mesh boxes directly on the seafloor, right next to active vent communities. The mesh was fine enough to block the larvae swimming in the open water, but if the theory of a subseafloor highway was correct, it would do nothing to stop larvae traveling beneath the crust. The boxes were like listening devices. If new life appeared inside them, it could only have come from below. For a year, the boxes sat on the seafloor, in the eternal dark, while the team waited. The ocean above them churned with storms and calms, completely unaware of the silent experiment happening 2 miles beneath its surface. When the team returned, the recovery was a meticulous, nerve-wracking process. The robotic arm on their submersible reached out, its grip closing carefully on the steel frame. As it lifted the box, the intention was to leave the mesh behind, to see what had colonized the area underneath. But the ocean floor had other plans. The volcanic crust had glued itself to the mesh. And as the arm pulled, it didn't just lift the box. It peeled back a section of the seafloor itself. It was a moment of beautiful, chaotic accident. A moment that tore back the veil. Beneath the crust was not solid rock. It was a cavity, a hidden chamber, just inches high, filled with clear, warm water. And inside that chamber, thriving in their secret sanctuary, was an entire community. White, grazing snails, the wriggling, predatory forms of scale worms, and most importantly, the delicate, flower-like tips of young tube worms. They were not on the seafloor. They were under it. This was not a fossil. This was not a theory. This was a living, breathing ecosystem hidden in the basement of the world. The subseafloor biosphere was real. The larvae didn't just travel through this labyrinth. They lived in it. They grew in it. This was their nursery, their protected highway, their true home. The ocean we thought we knew was merely the top floor of a skyscraper, and we had just discovered that every floor beneath it was teeming with life. The discovery was profound, but it was also local. A single torn-open cavity on the Pacific floor. The immediate, staggering question that followed was one of scale. Was this a rare, isolated pocket? Or was it a single window into a global phenomenon? Was the entire ocean floor, from the frigid North Atlantic to the roaring Southern Ocean, resting on top of a second, hidden ocean? The answer would require looking not at the mud and the rock, but at the data from the void above it. The proof would come from satellites, looking down from space to see the breadth of the world beneath the waves. The proof was not going to be found by looking down, but by looking up. From the sterile silence of space, a new generation of sentinels began to watch our planet with an unblinking precision gaze. Satellites like NASA's GRACE and the European Space Agency's Cryosat were not designed to find hidden oceans. Their mission was to measure the infinitesimal, the subtle pull of gravity variations, the rise and fall of ice sheets by millimeters. But data, in the hands of curious minds, has a way of revealing secrets it was never meant to tell. As these satellites passed over the vast, unbroken plains of the ocean, their lasers and radars detected a faint, impossible signal. The seafloor itself was moving. It was not a dramatic heave. It was a slow, rhythmic pulse. In some regions, the bedrock beneath the ocean was rising. In others, it was falling. The pattern was not random. It matched the predictions of the hidden ocean theory perfectly. The cause was poroelasticity, a simple concept describing how a porous material, like the oceanic crust, rebounds when the fluid within it drains away. The satellites were detecting the literal breathing of the subseafloor ocean. As massive volumes of water flowed through the crust's labyrinth, the rock would inflate and deflate in a slow-motion heartbeat. The scale was staggering. This was not a handful of isolated aquifers. This was a global system, a continuous layer of water-saturated rock underlying the entire ocean basin. The data painted a picture of a planet alive with subterranean hydrology. Scientists began to identify specific, massive water reservoirs. One of the largest was discovered off the coast of New Zealand, where a section of the Pacific Plate alone was calculated to hold a volume of water equivalent to several Amazon rivers. But how does the water move? The driving force is the relentless engine of plate tectonics. As oceanic plates are born at mid-ocean ridges, they are hot and porous. Seawater is pulled down into this young, thirsty rock. As the plate ages and moves away from the ridge, it cools and is pushed deeper at subduction zones. This process squeezes the water out, like a giant geological sponge. The water, now superheated and rich in minerals, is forced back upward, fueling the vent ecosystems and creating the vast, interconnected flow that the satellites detected. The final visual proof came from the seafloor itself. Using deep-towed sonar systems, research vessels began to map the abyssal plains in unprecedented detail. The images that came back were not of smooth, featureless mud. They revealed a landscape pockmarked with thousands upon thousands of circular depressions, like dimples on a golf ball. These are pockmarks, the exhaust vents of the hidden ocean. From these features, a slow, steady flow of fresh, chemical-laden water seeps out, not with the violent fury of a hydrothermal vent, but with a constant, widespread whisper. This is the discharge point of the subsea flow. This is where the hidden ocean breathes out, influencing the chemistry of the deep sea and providing a constant, diffuse food source for life across vast areas of the seafloor. We were no longer looking at isolated oases. We were looking at a fertilized plain, its fertility governed by the world below. The discovery was now complete. We had the theoretical framework, the accidental revelation of the ecosystems, the satellite proof of the global pulse, and the geological evidence of its discharge. The hidden ocean was real, vast, and teeming. But with this monumental discovery came a sobering realization. This ancient, interconnected world, which had shaped the evolution of life on our planet for eons, was no longer a secret we alone possessed. Our own species had stumbled upon its threshold. And we brought with us not just curiosity, but drills. We have pulled back the crust and found a new world. But discovery is a double-edged sword. The same moment we grasp the magnitude of this hidden ocean, we must confront our capacity to destroy it. This is not a remote, abstract ecosystem. It is the foundation of the deep sea, the nursery for the vents, and a vast, living reservoir of microbial life that influences the very chemistry of our planet's oceans. And it is now in the crosshairs. The deep-sea mining industry is poised to begin. Their target, polymetallic nodules, potato-sized nuggets of rare metals that litter the abyssal plains. To harvest them, they would send colossal machines to scrape the top 5 to 10 centimeters of the seafloor, precisely the layer that forms the ceiling of the hidden ocean. The consequences would be catastrophic and utterly irreversible. The scraping would not just destroy the pockmarks and seepage points. It would compact the porous crust, collapsing the intricate labyrinth of cavities. It would smother the entire subseafloor highway in a thick, toxic blanket of sediment. The larvae traveling beneath the crust would be entombed. The nurseries would be obliterated. The scale of this destruction would be continental. A single mining operation could claim an area the size of a major city each year. And this is not a localized event. The sediment plumes created by these machines would be carried by currents for hundreds of miles, raining a slow death over a much wider area. This is not merely mining. It is clear-cutting the basement of the global ocean. In a world of increasing noise, there is a profound value in preserving the artifacts of human discovery. The journals of the HMS Challenger, the dive logs of the Alvin. These are not just records. They are touchstones to moments that changed our understanding. In my own work, I value tools that are built with that same spirit of enduring quality and thoughtful design. That's why I rely on Curio Collector. Each of their handcrafted journals and timepieces is a testament to preserving what matters. They believe that in a disposable age, some things should be built to last, to remind us of where we've been, and to inspire where we're going next. But the implications of this discovery ripple outward, far beyond the immediate threat. The existence of this vast, hot, dark biosphere forces us to look at our solar system with new eyes. For decades, the prime candidates for extraterrestrial life were Mars or the cloud tops of Venus. But the true analogues to the subseafloor ocean are not planets. They are icy moons. Jupiter's moon Europa and Saturn's moon Enceladus. These are worlds encased in a global shell of ice, beneath which strong evidence suggests vast liquid saltwater oceans slosh against a rocky volcanic core. They are, in essence, planetary-scale versions of what we have just found on Earth. The discovery of a thriving intraterrestrial ecosystem on Earth gives us the blueprint, the biological confidence to say that life on these moons is not just possible, but perhaps probable. The same chemistry, water, rock, and heat that powers the hidden ocean on Earth could be powering life on Europa. We are no longer searching for little green men. We are searching for blind, white worms in an alien abyss. The hidden ocean has rewritten the rules for the hunt for life in the universe. We are not alone. We are likely surrounded by water worlds, each one a potential sanctuary for life. We began this story with a blank space on a map, and the words, "Here be dragons." We end it with a fundamental truth. The dragons were real. They were not monsters of scale and fury, but ecosystems of sublime and fragile complexity, hidden in the rock beneath the sea. The ocean that shouldn't exist on any map does exist. It is a global, living entity, a testament to life's relentless ingenuity. It is a world that has nurtured the deep sea for eons, and it may hold the key to finding our cosmic neighbors. But this giant is no longer sleeping. It is stirring to our presence. The question is no longer what is down there. The question is what we will do now that we know. Will we be the guardians of this last great frontier, or the force that silences its breath forever? The final chapter of this story has not been written by science. It will be written by us,